four polypeptide chains present in hemoglobin. So each hemoglobin carries four oxygen molecules. Four oxygen molecules. Each hemoglobin carries four oxygen molecules. HbO2 four times. If the hemoglobin carries one oxygen molecule, that is 25% saturation. If the hemoglobin carries two oxygen molecules, 50% saturation. Three oxygen molecules, 75% saturation. Four oxygen molecules, 100% saturation. Each hemoglobin carries four oxygen molecules. 4 oxygen plus Hb gives rise to Hb, 4 oxygen molecules. If the one hemoglobin carries one oxygen, 25% saturation, two oxygens, 50%, three oxygens, 75%, four oxygen molecules, 100% saturation. This is oxygen hemoglobin dissociation curve. What is oxygen hemoglobin dissociation curve? The relation between partial pressure of O2 and hemoglobin saturation. Partial pressure of O2 plotted on x-axis. Hemoglobin saturated, percentage of hemoglobin saturation plotted on y-axis. This is 10 mm Hg, 20 mm Hg, 30, 40, 50, 60, 70, 80, 90, 100. X-axis. Saturation 10%, 20%, 30%, 40%, 50%, 60, 70, 80, 90, and 100%. At 100 mm Hg partial pressure of O2, at 100 mm Hg partial pressure of O2, 100 mm Hg partial pressure of O2, hemoglobin saturation is 97%. Here, 97%. At 100 mm Hg partial pressure of O2. Next, at 40 mm Hg partial pressure of O2. At 40 mm Hg partial pressure of O2, saturation is 75%. And to delivery of oxygen is maximum 97. 97 minus 75 is equal to 22%. At 40 mm Hg partial pressure of O2, saturation is 75%. Delivery of oxygen and dissociation of oxyhemoglobin is 22%. This is oxygen hemoglobin dissociation curve. It is a sigmoid curve. In the lungs, partial pressure of O2 and pH or more, and high partial pressure of O2 and high pH. Low pCO2 and low H plus ion concentration and temperature. These are the conditions in lungs. In the lungs, high partial pressure of O2, high pH, low CO2, low H plus and low temperature. Under these conditions, oxygen combines with the hemoglobin. Here, lungs, partial pressure of O2 is high, that is 104. Lungs, oxygen combines with the hemoglobin and forms the oxyhemoglobin. Oxygen, it is in the form of oxyhemoglobin. Oxyhemoglobin. Near the tissues, in tissues, conditions are quite opposite. That is, partial pressure of O2 less or on a low pH, high CO2, partial pressure of CO2, high H plus ion concentration and high temperature. Under these conditions, oxyhemoglobin dissociates into oxygen and hemoglobin. Here in the lungs, oxygen combines with the hemoglobin and forms the oxyhemoglobin. Whenever the oxyhemoglobin reaches the tissues, the conditions are quite opposite. Due to these conditions, oxyhemoglobin dissociates into oxygen and hemoglobin. Oxyhemoglobin dissociation curve is a sigmoid curve. When this curve moves towards the x-axis or away from the y-axis or towards the y-axis or away from the x-axis. If the conditions are partial pressure of O2, pH high, this oxygen hemoglobin curve moves towards the y-axis. If the conditions are high pCO2, high H plus and high temperature, this curve moves towards the x-axis. That means towards the x-axis or left to right, towards the right. That means in tissues, blood, low pH, high CO2, low pH, high CO2. What are the conditions occur in the tissues, blood conditions? Low pH, high pCO2. In the lungs, high pH, low CO2. High pH and low CO2 are the conditions suitable for the formation of hemoglobin. Once again, high pH and low CO2 are the conditions suitable for the formation of oxyhemoglobin. Low pH and high CO2 are the conditions suitable for the dissociation of oxyhemoglobin. And finally, at 100 mmHg partial pressure of O2, 100 mmHg partial pressure of O2, saturation is equal to 97%. when the blood moves towards the tissues, partial pressure is decreases. Partial pressure of O2 decreases. At 40 mmHg of partial pressure, saturation is 75%. That means dissociation 22%. 22% of the oxygen deliver the tissues. Remaining oxygen is reserved in the blood for further requirements. In the case of athletics or sportsman, the muscles like striated muscles in which at 20 mmHg partial pressure, the saturation is 35%. Saturation is 35%. Special cases. At 20 mmHg partial pressure of O2, saturation is 35%. That means dissociation is 75 minus 35, or 97 minus 35, 62%. 62% dissociation, 35% saturation. Special cases. At 100 mmHg partial pressure, 97% saturation. At 40 mmHg, that means we move from lungs to tissues, partial pressure of O2 gradually decreases. 40 mmHg. At 40 mmHg, saturation is 70%, dissociation is 22%. That is about oxygen hemoglobin dissociation curve and also O2 transport. And last one, near the tissues, the conditions like high hydrogen concentration and high CO2 and high hydrogen concentration. The concentration of He plus and partial pressure of CO2 affect the affinity of hemoglobin with oxygen. That effect is called Bohr effect. What is Bohr effect? The effect of CO2 and H plus ion concentration on the affinity of O2 with the hemoglobin is called Bohr effect. Transport of CO2 takes place through three ways: plasma, carbamino compounds, and third one is bicarbonates. First one is plasma, dissolved state. 7% of the CO2 transport takes place through the dissolved state. 20 to 25% carbamino compounds. 70% of the CO2 transport takes place through the as bicarbonates. First one is as plasma. Carbon dioxide combines with the water of the plasma to form the H2CO3 carbonic acid near the lungs, dissociating to CO2 and H2O. Here tissues, carbon dioxide released. Carbon dioxide combines with the plasma, the water of the plasma, and forms the H2CO3. This H2 will reach near the lungs, dissociating to CO2 and H2O. Very least percentage of carbon dioxide transport takes place as solutes. And second one, carbamino compounds. About 20 to 25% of the carbon dioxide transport takes place through the carbon as carbamino compounds. NH2 or amino group of hemoglobin. Carbon dioxide combines with the amino group of hemoglobin and forms the carbamino hemoglobin compounds. Carbamino hemoglobin compounds. About 20 to 25% transport takes place. Major transport of CO2 as bicarbonate 70%. In the tissues, carbon dioxide released into the plasma. In the plasma, carbon dioxide from the plasma tissues, plasma. Next, RBC. In the RBC, this is the RBC. Carbon dioxide enter into the RBC. Carbon dioxide combines with the water of the cytoplasm of the RBC to form the H2CO3. Carbon dioxide combines with the water of the cytoplasm of the RBC to form the H2CO3, carbonic acid. In the presence of carbonic anhydrase, Ca, carbonic anhydrase. Immediately, this H2CO3 dissociates into He plus HCO3 minus. This H plus combines the hemoglobin and forms the HHB in the RBC. This is the plasma lemma or cell membrane of the RBC. It is impermeable to cations, permeable to anions. So HCO3 from RBC enter into the plasma. This is plasma. HCO3 enter into the plasma. That means anions enter into the plasma. To compensate the anions in RBC, some of the chloride ions, Cl minus ions from the plasma enter into the RBC. This is RBC and this one is plasma. The exchange of HCO3 minus and Cl minus ions between RBC and plasma is called chloride shift. Chloride shift. What is chloride shift? The exchange of HCO3 and Cl minus ions between RBC and plasma is called chloride shift. Here, this is the tissue. The tissue CO2, from the tissue, CO2 is entered into the plasma. From plasma to RBC, tissue plasma to RBC. In the RBC, carbon dioxide combines with the CO2 and forms the H2CO3. It is a fast reaction due to the presence of carbonic anhydrase. Immediately dissociate into H plus and HCO3 minus, bicarbonate ion, H plus ion. H plus ion combines the RBC, the hemoglobin of the RBC, forms the HHB. HCO3 enter into the plasma. To maintain the equilibrium, Cl minus ions from the plasma enter into the RBC. That means here anions, exchange of anions. The exchange of Cl minus and HCO3 minus ions between RBC and plasma is called chloride shift. So chloride shift is related to O2 transport or CO2 transport, CO2 transport. In the plasma, this HCO3 minus combines with the sodium or potassium to form the sodium bicarbonate NaHCO3 or potassium bicarbonate. Sodium bicarbonate or potassium bicarbonate. In plasma, CO2 is in the form of bicarbonate ion. Bicarbonate, sodium bicarbonate. Here is formed the sodium bicarbonate. This sodium bicarbonate near the lungs. When they reach the lungs or near the lungs, this one also RBC, this is also RBC. This HCO3 minus dissociates into HCO3 minus and Na plus. HCO3 enter into the RBC. In the RBC, Cl minus ions. Cl minus ions enter into the plasma. Then near the lungs, exchange of HCO3 minus and Cl minus ions between plasma and RBC takes place. That is called reverse chloride shift. Reverse chloride shift occurs near the lungs. Chloride shift occurs near the tissues. Chloride shift near the tissues. Here chloride shift. Here reverse chloride shift. Then HCO2 enters the RBC, then combines with the H plus to form the H2CO3. H2CO3. Dissociate into H2CO3, dissociate into CO2 and H2O. CO2 and H2O. This CO2 enter into the plasma, and from the plasma lungs and outside or atmosphere. Once again, tissues, CO2 from the tissues enter into the plasma. From the plasma, RBC. In RBC, carbon dioxide combines with the water of the cytoplasm of the RBC to form the H2CO3 in the presence of carbonic anhydrase. It dissociates into HCO3 minus and H plus. H plus combines the HB and form the HHB. This HCO3 ion or bicarbonate ion from the RBC enter into the plasma. To compensate this, Cl minus ions enter into the RBC. This is called chloride shift. Exchange of HCO3 and Cl minus ions between RBC and plasma is called chloride shift that occur near the tissues. HCO3 combines with the sodium or potassium to form the sodium bicarbonate or potassium bicarbonate. CO2 is in the form of bicarbonate ions in the blood. Near the lungs, immediately enter into the RBC. In the RBC, HCO3 combines with the H plus to form the H2CO3, dissociate into water and CO2. CO2 enter into the plasma. From the plasma, lungs. From the lungs passes outside. That is atmosphere. This is about transport of CO2. Transport of CO2. Chloride shift also called as Hamburger's phenomena or Hamburger's shift. Chloride shift or Hamburger's. Bohr effect is related to O2 transport. Chloride shift is related to CO2 transport. Okay.